Hello. In this session, we will discuss about temperature dependence of reaction rate. Precisely, there is a theory for that to explain the temperature dependence of reaction rate. That theory is called Arrhenius Theory. We will discuss that Arrhenius Theory, and we will also discuss about activation energy. So, it has been observed that rate of chemical reaction almost always depend upon temperature. Here, there are three graphs. All the three graphs shows the rate of chemical reaction with respect to temperature. The y-axis is rate of chemical reaction and the x-axis is temperature. We can observe that with increase in temperature, the rate of reaction increases. For various kinds of reaction, we will see we will understand what is A type reaction, what is B type reaction, and what is C type reaction. A type reaction is the most commonly occurring reaction type where reaction increases exponentially with reciprocal of the temperature. As the temperature increases, the rate increases. And what is the exact behavior? The rate of reaction increases exponentially with reciprocal of temperature, that is 1 over T. Now what about the B type reaction? B type reaction is an explosive reaction after certain threshold temperature. When the temperature reaches a threshold value, up to a certain threshold value, the rate of reaction increases with increase in temperature. Again, further this increase is exponential in nature. But after that threshold temperature, what happens? There is an explosive jump in the reaction rate. Means the rate of reaction increases suddenly after that threshold temperature. This is explosive reaction. This is a explosive reaction. And what is the reaction type C? The reaction type C is an enzyme controlled reaction where enzyme becomes deactivated at high temperature. Now in enzyme catalyzed reaction, the rate of reaction increases with increase in temperature. After certain temperature range, after around 50 or 60 degrees Celsius, generally I am speaking, the enzyme becomes denatured. Enzymes are nothing but proteins, and the proteins break down. Protein starts breaking down after a certain high temperature, and they starts opening up, and the enzyme activity decreases. Therefore the rate of reaction drops down suddenly. So these are the three expressions where rate of reaction and their temperature dependency is explained. Now in all the cases, up to a certain temperature range, the rate of reaction increases with increasing temperature. We will not discuss the explosive reaction and we will not discuss the enzyme reaction right now. We will discuss the general category of reaction where rate of reaction increases exponentially with increase in temperature. Now experimentally it has been observed that for many reactions, a plot of ln k is the rate constant versus temperature inverse, okay, 1 over T gives a linear graph, okay, or close to linear response. So experimentally it has been found that a plot of ln k versus T inverse or 1 over T gives a linear graph. This is experimentally observed. Now based on this experimental observations, Arrhenius generated an empirical relation between temperature and rate constant K. It has been observed that ln k and T inverse gives a straight line response. So Arrhenius, from many experimental observations, Arrhenius developed an empirical relation. The empirical relation goes like d ln k over dt is equal to EA over RT square. I will explain what is EA. Now integration of above expression gives ln k is equal to ln A minus EA over RT. Again I will say what is A. Or we can also write the second expression as k is equal to A e to the power minus EART. Now there are two new terms. One is A, that is capital A, and the other is EA. Okay, A is called Arrhenius pre-exponential factor or frequency factor. It is a constant quantity. Okay, then EA is the activation energy. EA is the activation energy of the reaction. It varies from reaction to reaction. R is the universal gas constant. T is the absolute temperature. K is the rate constant. EA is the activation energy of reaction. A is referred to Arrhenius pre-exponential factor or frequency factor. Activation energy is the threshold energy required for a chemical reaction to occur. So if the reactant molecules don't have sufficient activation energy, they will not form product. So unless and until the reactant molecule possesses certain activation energy, then the product formation is not possible. So for any product to form, the reactant must sufficiently possess the energy which is greater than or equal to the activation energy of the reaction. Now at two different temperatures, if we work with this expression at two different temperatures, the expression for rate constant can be obtained. So the expressions for rate constant at two different temperatures is given as log K2 over K1 is equal to EA over 2.303 R T2 minus T1 then over T1 into T2, or in form of natural logarithm we can write ln K2 over K1 is equal to minus EA over R 1 over T2 minus 1 over T1. This minus should be taken care of because I have subtracted 1 over T2 minus 1 over T1. T1 is the temperature at first state and temperature is second state. Similarly, K2 and K1 is the rate constant for the second state and rate constant for the first state respectively. EA is the activation energy of the reaction. Now there is an important point to remember. The unit of pre-exponential factor or frequency factor or Arrhenius pre-exponential factor is identical to the rate constant and varies depending upon the order of reaction. Here in this expression, in this second expression, we see ln K is equal to ln A minus E over RT. From this expression, what will be the unit of A? That is the pre-exponential factor or Arrhenius pre-exponential factor or frequency factor. The unit of A will be same as unit of K. From the unit dimension exercise of physics classes, we know that from this expression that the unit of A, that is the frequency factor, will be same as unit of rate constant K. Again, the unit of rate constant K varies from different reaction types. For a first order reaction, the unit of rate constant is time inverse. For second order reaction, it is different. For zero order reaction, it is different. Similarly, the unit of rate, the frequency factor will be different for different types of reaction. But the unit of rate, the frequency factor is same as the unit of rate constant. That is the first important point to note. The second important point to note that unit of activation energy is energy per mole or energy mole inverse. This minus 1 should be superscript. So energy per mole is the unit of activation energy. Now precisely the unit of activation energy can be kilojoule per mole or joule per mole or kilocalorie per mole or calorie per mole, like that. Now we'll from this expression, second expression, we can treat this second expression as a straight line expression. Suppose y is equal to straight line equation is y is equal to mx plus c. Here y axis is ln k, mx is this x axis is 1 over t. So what will be my slope? My slope will be minus ea over r. My slope will be minus A over R, and what will be the C-intercept? The C-intercept will be ln A. So if I draw a plot, if I draw a graph between ln K and 1 over T, I'll get slope is equal to what? Minus E over R, and Y-intercept as ln A. So from if I have data points and if I draw a graph, if I know that if I follow the reaction kinetics for different temperatures, then using those data points, if I draw a plot, then I can find out what is the activation energy of the reaction. I can also find out what is the Arrhenius pre-exponential factor from the y-intercept. The slope will inform me about the activation energy. The y-intercept will inform me about the frequency factor or Arrhenius pre-exponential factor. Now we'll understand all about the activation energy from this graphical representation. Here the reactants are at a certain lower temperature and product has lower energy profile, and products are at a higher energy profile, and this is the reaction coordinate. So it may so happen that it is mostly the case that reactants are at higher energy and products are at lower energy, but that does not matter. Reactants are going to form products, and they have to pass a certain activation energy barrier. Okay, this energy barrier, unless and until the reactants possess this energy barrier, activation energy barrier, the products will not be formed. Now this I'll represent this activation energy barrier and the energy distribution of molecules. In the left hand profile, the left hand graph shows the Boltzmann distribution of energy of molecules, energy of reactant molecule. The right hand profile shows the activation energy. So activation energy, this dotted line shows the activation energy. Okay, and now we'll understand this left hand curve. This left hand curve shows the Boltzmann distribution of molecular energy of reactants, means how the molecular energy of reactants is distributed. The two curves are two temperatures. Now at low temperature is 200 Kelvin, the high temperature is 500 Kelvin. And the red line shows the high temperature graph and the blue line shows the low temperature graph. So we see when the temperature increases, the molecular energy of the reactants increases. You see here when you go up, the energy is increasing. So as the temperature increases, the molecular energy increases. As the temperature decreases, molecules with low energy increases. At low temperature, molecule with low energy is more. The area under the blue line is more at low energy region. Similarly, the area under the red line is more at high energy region. So as the temperature increases, the reactant energy increases, and now this dotted line is the activation energy. So only those reactant molecules which have higher activation energy will react to form product. So we'll compare what are the number of molecules that is present above, that have energy above this activation energy. So we see at higher temperature, this is the red line, more molecules are having the sufficient energy to cross this activation energy barrier. But at low temperature, that is at 200 Kelvin, there is very minimum amount of reactant molecules are there which possess energy greater than this activation energy. So I can precisely say that as the temperature increases, the Maxwell-Boltzmann distribution of molecular energy, which is greater than the activation energy, increases, and the probability that more and more reactants will form product increases with respect to increase in temperature. So this is all about the Arrhenius expression and the activation energy. For most of the reaction, the temperature most of the reaction follow Arrhenius expression. Means when we plot a graph between ln k and t inverse, we get a straight line response. However, there are certain reactions where Arrhenius expression is not followed. To explain such reactions where Arrhenius behavior is not followed, modern theories of reaction rate predict the rate constant, and the rate constant expression is given as k is equal to, for Arrhenius case it was k is equal to a exponential minus Ea over RT. Now when for certain reactions where Arrhenius behavior is not followed or Arrhenius expression is not followed, the rate constant is given as k is equal to a t to the power m e to the power minus e prime over RT. This is a new expression for the rate constant for those chemical reactions where Arrhenius expression is not followed. Now there are 2-3 important terms here. T is the temperature, absolute temperature. A is a new thing, M is a new thing, and E prime is a new thing. So we'll see what is A, M and E prime. A and E prime are temperature independent quantities. Okay, and M can have values 1 or 0.5 plus 0.5 or minus 0.5. M can have values minus 0.5, 1 or 0.5, and the values of M depends upon the theory used to predict the rate constant. There are many theories possible to predict the rate of reaction or rate constant of the reaction. So depending upon which theory we are using, M will have certain value. So for an example, in activated complex theory, we will not discuss this activated complex theory, which is beyond the scope of this syllabus. So in activated complex theory, M is taken to be 1. For other kind of theories, M can be minus half or plus half. So in activated complex theory, M will be equal to 1, and A is also an temperature independent quantities. So this expression, this rate constant expression, is applicable to for reactions which are not following Arrhenius kind of behavior. So with this I'll stop here. Next session we'll discuss about collision theory and absolute reaction rates. Thank you.